Hi there, grade sevens. Today is our science day, and we're going to take a closer look at the particle model, temperature, and thermal energy. We've been discussing over the past couple of weeks a little bit about heat, temperature, and energy, and so we're going to take an even closer look today. First thing I want you to do, I want you to try waving your hand in the air, just like this. Now, as you're doing that, I want you to think about what it would be like if your hand was moving through water. Would it be the same or would it be different? Is it easier or more difficult? Now, what if you tried to move your hand through wood or steel? How difficult would that be? And think to yourself, why would it be more difficult or less difficult? Moving your hand through air is easy because the particles that make up air are spaced far enough apart. Your hand is able to easily move them aside. Now, why might that type of movement be more difficult where the other substances are concerned? First, you should know that the particles in all matter are extremely small. You might be sort of thinking to yourself, well, what do you mean by extremely small? I mean, that could mean a couple of different things. A mouse is extremely small. Is that what we mean about these particles? Well, I want you to imagine a drop of water balanced on your fingertip. How many individual water particles do you think are clinging together to create that one drop? The answer is actually 1,700 million. Okay? No wonder you can't see those particles without a microscope. You can't see it with your eye. They're just way too tiny. And so that's what we mean by extremely small. They are really, really tiny. The particle model of matter is a scientific description of many different types of features of these very tiny particles. Three of the most important ideas of the model are: all substances are made of tiny particles that are too small to be seen. The particles are always in motion, so they're either vibrating, rotating, and in the case of liquids and gases, moving from place to place. The particles also have spaces between them. As you probably noticed in the last activity, if the motion of the particles in a substance changes, the temperature of the substance changes too. So when a substance warms up, or when its temperature increases, its particles are moving faster. When a substance cools and when its temperature decreases, its particles are moving more slowly. Now, this idea is what forms the basis for the fourth point in the particle model. It states the motion of the particles increases when the temperature increases. The motion of the particles decreases when the temperature decreases. It's not really easy to test this idea directly. And as you now know, the smallest particles of matter are way too tiny to observe very clearly. They can be observed only in large groups. In any substance, some particles always seem to be moving faster than average. Other particles seem to be moving unusually slow. The average speed of many particles, however, is always indicated by their temperature. So temperature indicates the average speed of particle motion in a substance. Energy is a measure of something's ability to do work. So, in other words, it causes changes. Whenever something happens, scientists are sure that energy is being transferred from one thing to another. Let's think of some everyday type of examples. I want you to study the pictures on page 204 of your textbook. And I want you to try to describe 3 features of each situation. As you're taking a look at those pictures, I want you to think to yourself, what has high energy? What has low energy? What change is being caused as energy is transferred? And what source provides energy for the change? To what is the energy being transferred? Hot air balloons, ovens, a hot tub. These and many other types of devices are designed to release and transfer thermal energy, so energy associated with hot objects. The fuel in a hot air balloon burns, transferring thermal energy to air, which warms, expands, and lifts the balloon. Hot metal elements in an oven transfer thermal energy to food, warming and cooking it. Hot water in a hot tub transfers thermal energy to people in the tub. Have you noticed the same 2 features of each energy example? You can identify them in any situation where change is occurring. So number 1, changes happen when there is a difference of energy. Every useful energy system has a high energy source that powers the changes. And number 2, energy is always transferred in the same direction, from high energy source to something with a lower energy source. Does your bedroom get chilly on cold winter nights? In just a few minutes, a small electric heater can warm the room up. The heater transfers thermal energy to the air. The air particles move faster as their average energy increases, and you can notice the temperature rising. Now, imagine trying to warm a very large building, maybe like a huge gymnasium, using the same small heater running for the same amount of time. What happens? Does it warm it up the same way? No, it seems like almost a hopeless task. The same amount of thermal energy would be transferred to the air, but in the larger room, there are many more air particles. And so each particle gets only a tiny share of the extra energy. The average energy of the particles increases, but only a very tiny bit. So the air temperature rises, but not very much. You can see that there's a connection between thermal energy and temperature. Heating anything increases the total energy of all its particles. The average energy of the particles, or the temperature of the substance, may increase a little or a lot. The temperature change depends on the number of particles, or that is the amount of material that you're heating. Now, what about cooling? Imagine putting an ice cube in a glass of warm lemonade. The ice absorbs thermal energy as it melts. With less energy, the average motion of the particles in the lemonade slows down, and the temperature of the lemonade drops. Could the same ice cube cool off a bath or a hot tub filled with steaming water? Hardly. The ice would absorb the same total amount of thermal energy as it melted. The average energy of the particles would drop, but only a tiny bit because there are so many of them. Again, the temperature change depends on the amount of material as well as on the change in thermal energy. I just don't have enough energy to do my homework. I'm so hungry. I need a big meal to get enough energy for the soccer game. You look exhausted. Did cleaning your room use up all your energy? Energy is not a substance. It can't be weighed. It doesn't take up space. Energy describes a quality or a condition. So think about words that describe other qualities or conditions. You might describe the drums in a band as loud, but that doesn't mean that they're filled with extra loudness. If a guitar is played softly, that doesn't mean that its loudness is almost used up. So what is energy? Well, energy is a property or quality of an object or substance that gives it the ability to move, to do work, or to cause changes. Energy is the topic of one of the most important laws of nature. The law of conservation of energy states, energy cannot be created or destroyed. It can only be transformed from one type to another or passed from one object to another. Is it still okay to say, wow, I'm feeling full of energy today? Of course, everyday language is fine for everyday life, but just remember to be more precise when you're giving a scientific description.